Hi, welcome to this video. So here's a problem regarding heat transfer. So we have a 0.5 meter diameter pipe with emissivity of 0.9. So the pipe carrying steam has a surface temperature of 500 K. The pipe is located in a room at 300 Kelvin, and the convection heat transfer coefficient between the pipe surface and the air in the room is 20 watts per square meter K. Calculate the following: A. Combined heat transfer coefficient, and B. The rate of heat loss per meter of pipe length. So for our solution, so we need to illustrate this for us so that we can easily analyze this problem. And so we have a 0.5 meter diameter pipe. So let's draw some pipe. So this pipe here is 0.5 meter in diameter. So this diameter of the pipe is 0.5 meter, and the emissivity of this pipe, so there's a uh, radiation because there's an emissivity of the pipe is given. So the emissivity of this pipe is 0.9. Okay, so this pipe here says that it carries a steam. Since there is a steam flowing inside this pipe, which results to a surface temperature of 500 K. So the temperature here, the surface temperature here is the surface of the pipe is 500. So we have 500 Kelvin. Okay. So let me color it as red because the steam is hot. And the pipe is located in a room, so let's draw the room. Say this is our room. In the room, say this is our room. Room temp is 300 K. So the surface is much higher in temperature than the room. And the convection heat transfer, so there is a convection heat transfer between this surface and the room, that with a H value of, or the heat transfer coefficient of 20 watts per quiz. So we have Q and we have, so let's draw the heat transfer. You have Q convection and Q radiation. Okay. Our heat transfer coefficient, convective heat transfer coefficient, is 20 watts per meter square K. Okay. So having this information, let's calculate the combined heat transfer coefficient. Since we have the combination of the convection and radiation here, so we need to determine the combined heat transfer coefficient, or H. Okay. So we can also illustrate this using the resistance, say from surface, which is 300K, I mean 500K, then we have 2 H, the convective, and from radiation. Then we have here the room temperature, which is 300K. Okay, so we have two modes of heat transfer. Okay, so to solve for this, combined heat transfer coefficient, or H, can now calculate this using the formula. H is equal to the heat transfer coefficient of convection plus radiation, or HR. Okay, so say this is our equation 1. And by looking at this equation, we already have the value of this HC, where HC is given. So this is given, or in HC is equal to 20 watts square meter K. So we need to determine the value of HR. In to solve for HR, our formula is the emissivity times the Stefan-Boltzmann constant times the temperature 1 raised to 4 minus the temperature 2 raised to 4 also. Okay, so we have the value of this emissivity. The pipe emissivity is 0.9. This one 0.9, so we can substitute it here. So we have 0.9, and then our Stefan-Boltzmann constant is equal to 5.67 times 10 to the negative 8 watts per meter square K to the 4th, right? So can now also substitute it here. So we have 5.67 times 10 to the negative 8 watts per meter square K to the 4th. And our T1 here is the temperature of the surface of the pipe, because that is higher than the room temperature. So our T1 is the TS, which is 500K. So we have 500K raised to 4 minus the T2, of course, is the room temperature, which is 300K raised to 4. So all in all, the value of our HR is 13.9. Our unit is watts per square meter K. Okay. So since we've already computed the value of our HR, we can now substitute the value of HR to our equation 1 to solve for combined heat transfer coefficient. So to solve for this one, okay, so we have H is equal to HC plus HR, wherein our HC is given, which is equal to 20 watts per square meter K, and our computed HR is 13.9 watts per yan. So all in all, the combined heat transfer coefficient from convection and radiation is 20 plus 13.9. We have 33.9 watts per square meter K. So that is for letter A, the combined heat transfer coefficient.